Hello, my name is Andrew Dillon. I am here today with Nathan Ching and Nicholas, and today we will be discussing the Physics 212 Project 1. The question we had decided to do was the first question involving the turntable. What it was asking us was if we had a box that we decided to label Mass 1 is connected at the end of a turntable right here. So if you see a top-down view, the box would most likely look like this. And if that is connected by an ideal string passing over a pulley right here, all the way here, and it goes through the turntable all the way down and is connected down at the bottom through a hollow ball that we decided to label mass 2. If that is connected, what is the angular speed of this turntable? A way to just easily describe it is to make two free body diagrams for this as well, where we have the first one, M1, which is the box right here, which would just have a normal force pointing up to counteract the force of gravity, a force of tension on the mass 1 by the string, and then also a force of gravity as well on the block by the Earth. And then for the other free body diagram, for the one right over here, we can just draw it here, label it M2, and then we would have a force of tension on the string on M2 by the string. And then we would have just a force of gravity as well on the Earth by the ball. And then we have to remember that it was given that M2 would be a hollow ball, while M1 would be a solid object. Our assumptions that have been given and what we can realistically assume are that the string connecting both right here, so the string right here, is going to be inextensible and it's going to just be an ideal string. The given angular speed of the turntable is going to be constant, so we aren't going to have to worry about that changing. And then we also believe that momentum should also be conserved because all what is happening within the system. I will now hand it off to Nicholas, who is going to be going through the solution.
Hi, I'm Nicholas Norlin-Pritchard. I'll be going over our solutions section. To determine the angular speed of the turntable, our group decided to work towards one equation, which is the centripetal acceleration equals the translational velocity squared divided by the radius. With the centripetal acceleration, we could substitute the translational speed v with the angular speed omega with the formula omega equals v divided by r. To do this, we needed to determine the torque acting on the string, as well as the force tension acting on the string by the hollow sphere, mass 2, to later determine centripetal acceleration. The only two forces acting on mass 2 are the force tension and the force of gravity. We can write this as the mass of the hollow sphere times the acceleration equals mass times gravity minus the tension force. We can then rearrange this to acceleration equals gravity minus the tension force divided by mass 2. Putting that aside, we know that the net torque acting on the string equals the moment of inertia times the angular acceleration. Since the tension force is the only force acting on our ideal string, we can substitute torque with the formula radius cross product force, where force will just be our tension force. Additionally, we can make changes to the moment of inertia times angular acceleration by replacing angular acceleration with translational acceleration divided by the radius, and replacing the moment of inertia with the formula that determines the moment of inertia for a hollow sphere, which is 2/3 the mass, m2, times radius squared. By isolating translational acceleration to one side, our equation equals 3/2 the force tension divided by mass 2. Next, we take the two equations that we solved for acceleration and set them equal to each other, and solving for the tension force. We find that the tension force equals 2/5 mass 2 times gravity. We then took this value for tension force and set it equal to centripetal acceleration times the mass of box 1. We then substituted acceleration for angular acceleration and substituted angular acceleration for omega squared times radius squared. Solving for omega arrived us at our solution, the square root of 2/5 mass 2 times gravity divided by mass times the radius. I will now leave it to Nathan to go over the sense making of our solution.
Okay, so to do our sense making for this equation, we can just check that our answer, omega is equal to square root 2/5 mg over mr is equivalent. That makes sense. So we know that radians are unitless, and since omega, which is angular velocity, is equal to radians per second, we can pretty much just turn it into 1/second, and then we can have the mass of the little mass is kg, the mass of the big mass is also kg, those cancel out. And then we have gravity, which is meters per second squared, and we have radius, which is just meters. And then those things cancel out too, and then we lose the 1/seconds is equal to square root of 1/second squared. And then of course we can take the square root of 1/second squared, and that is just 1/second. So that checks out. And then we can do some, special case analysis. So if little m is much smaller, or it's much greater than big M, then omega will be about infinity. And I guess this makes sense because if we think about the pulley, the big mass won't be able to pull down the little mass like much at all, which means that the turntable will keep spinning with the high angular velocity. But then the opposite can be said if we have big M is much greater than little m, and that will result in the angular velocity being about 0, and makes sense physically in our equation. And physically, in this situation, it'll make sense because the pulley, the hanging mass will pull down the little mass very quickly, which will result in a smaller angular velocity. And then we can think about as the radius of from the pulley to the little mass approaches 0. We can see that omega will be around square root 2/5 mg over m over big M. And then that makes sense because if we go over and we look at our solution, we see that centripetal acceleration is equal to v squared over r. And as r is almost 0, then the centripetal acceleration is just v squared, and that makes sense in our end result. And then we can look at the opposite and say if the radius is approaching infinity, the angular velocity is about 0. And then we can use that same centripetal acceleration, this like analysis. So if r was infinity, then the centripetal acceleration would be around 0, which would make sense in our final answer.
Hi, my name is Andrew Dillon, and today I will be covering the conclusion and reflection portion of our project. In conclusion, we used a variety of different problems that we have already looked at, either in lecture, homeworks, or studio projects, to get a better understanding on how to finish this question for our project. We used a variety of different questions, the first one being homework 3, problem 3, which asked us to find the acceleration of both masses and of the pulley connected to each other. This is very similar but also different to our project question, where it had, for the project, it now was on a turntable that rotated at a constant angular speed, and instead of an M2 here being just a block, it would actually now be a hollow ball that is wrapped around with a string or radius r. The main difference also is of homework 3, we did not need to calculate momentum, inertia. We didn't really have to do that much for that, but we did have to do it a lot more for our project because it is also rotating around. The second problem that we looked at was homework 4, problem 2, where it is now the disc brick system, where it's us trying to find the angular speed of that. We can see there it's going to be constant, which is pretty much what it is going as well in the project, where it's rotating at a constant angular speed. So we just had to solve for angular speed as well for the project of the turntable. We can also know that because the system is isolated, momentum should also be conserved.